Okay, students, so of course we continue with our thermodynamics. Now we want to look at an important situation where enthalpy has a limitation that we must be aware of. Now let's say you calculated the enthalpy of formation of a compound at 298 degrees Celsius, or 298 Kelvin rather. Let's say 298 Kelvin, which is 25 degrees Celsius. Alright? What if you also try to determine the enthalpy of formation at, let's say, 400 degrees Celsius, right? Or 700 degrees Celsius. Would the enthalpy of formation be the same? The answer is no, and you'll see why. Now remember that enthalpy change is equal to internal energy change plus the effect of pressure and volume change, or volume and pressure changes, right? Where delta U, of course, is equal to Q minus P delta V, P delta V being the work component. Hence, delta H then could be equal to Q minus P delta V plus P delta V. That is where delta U has been substituted for by Q minus P delta V. Therefore, we can see clearly that delta H is equal to Q, right? Especially at constant pressure. That's where this is what allows us to say then that enthalpy change is equal to the constant pressure heat. Now, of course, given that delta H is equal to Q, we can also say then that delta H is equal to C delta T, seeing that Q is equal to C delta T. The problem is that, and of course, it would be constant pressure heat capacity. The thing is that heat capacity values vary with temperature. Heat capacity values are not independent independent of temperature, as suggested by classical mechanics, and this kind of marks one of the failing points of classical mechanics, because classical mechanics believes that heat capacity is independent of temperature, and this is a failing point of classical mechanics. So, as mentioned before, what this means is that if you're looking at, for example, the enthalpy of formation of a compound at 298.15 Kelvin, that enthalpy of formation value will be different at 320 Kelvin. Fortunately, this guy, Kirchhoff, has an equation. He developed an equation. Of course, we tend to just call him Kirchhoff, but it's really Kirchhoff. He's a German physicist. Now, his equation says that the new enthalpy change value, I should say, delta H2 is equal to delta H1 being the old enthalpy value, that is the enthalpy value at, let's say, 298 Kelvin, and now we are trying to calculate the new enthalpy change value at 320 Kelvin, which is delta H2, right? He's saying that the enthalpy change, right, the new enthalpy change, delta H2, is equal to the old enthalpy change, delta H1, plus the change in heat capacity, constant pressure heat capacity, in going from one temperature to the other, where T2 is the higher temperature and T1 is the lower temperature. So using this equation, you can calculate the new enthalpy value. Now, what is delta Cp? Delta Cp is a change in the heat capacity, the constant pressure heat capacity for the compounds in the reaction, the reacting species and the product species, where delta Cp is equal to N, which is the stoichiometric coefficients, N, sum of products of heat capacity of products, constant pressure heat capacity of the products, minus N times the sum of the constant pressure heat capacity of the reactants. Now, in the Kirchhoff equation given above, there's implicit assumption that there's not much variation in the Cp values, the constant pressure heat capacity values for the independent compounds. Now let's consider an example. Let's say we are looking at the vaporization of water. So we have 1 mole of water, of course, liquid, being converted to steam, of course, vapor. Now, given that delta H, the standard enthalpy of vaporization of water at 298 Kelvin is 44 kilojoules per mole. Of course, that will now be the old enthalpy value. And now you're asked, what is the value, what will the enthalpy of vaporization be at 100 degrees Celsius? Of course, that is 373 Kelvin. Of course, we're ignoring the 0.15 here, but right. Let's go ahead. Okay, so the heat capacity, constant pressure heat capacity value for water is 75.29 joule per Kelvin per mole, and this, as you can realize, this is a molar heat capacity value. And then now you have also the constant pressure heat capacity value for steam, which is 33.58 joule per Kelvin per mole. Now, when you calculate the difference between these two, of course, giving consideration to the stoichiometric coefficients in this equation, of course, the stoichiometric coefficient is 1, we have a delta Cp value of minus 41.71 joule per Kelvin per mole. Now, of course, it is interesting that we have a negative value, and this tells us clearly that as the temperature of water increase, then its heat capacity, its constant pressure heat capacity value will decrease. Now note that heat capacity cannot be negative. However, we did not calculate heat capacity, we calculated a change in heat capacity, and the change in heat capacity can be negative, as indicated by the results here of our calculation of delta Cp. So it can be negative, indicating that the final constant pressure heat capacity is lower than the initial constant pressure heat capacity. Now we can substitute those values, substitute the change in heat capacity value into Kirchhoff's equation, as well as the old enthalpy value, which is the enthalpy value at 298 Kelvin, which is 44 kilojoules per mole. As you can see here, we have basically put it in joules, and also we have included now our temperatures, and at the end of the day, our enthalpy change at 100 degrees Celsius is 40.87 times 10 to the 3 joules per mole. Alright, so that's our new enthalpy value, enthalpy of vaporization value for the conversion of water to steam. And we can see clearly that there is a decrease from 44 kilojoules per mole to just basically 40.87 kilojoules per mole. So there's a decrease in the enthalpy of vaporization as temperature increases, and this is as a result of a decrease in the heat capacity value, seeing that enthalpy change is directly proportional to heat capacity. Let's say the heat capacity values vary significantly, then one has to do a little bit of integration in addressing this problem. So we will have to consider the range of temperatures that we are dealing with, and so the Kirchhoff equation gets a little bit more complicated. Fortunately for us though, in practice, enthalpies do not vary greatly with temperature. So that's a good thing for us. That's a good escape route for us. But of course, we have to know that if they vary significantly, we have a way to address such a situation. Now, just some useful information here. At constant pressure, we know that Q is equal to Cp delta T, which is equal to delta H. We could rearrange that expression and we can realize that Cp is equal to delta H over delta T, which of course can be written as Cp is equal to dH over dt. Similarly, at constant volume, we know that Q, constant volume heat, is equal to CV delta T, which is equal to delta U, of course, because the internal energy of a system is the same thing as the constant volume heat. We can rearrange that expression and we can see that CV is equal to the ratio of internal energy change to change in temperature, which is the same as du over dt. And then we have some other useful information here, which basically at the bottom, which shows that Cp is equal to Cv plus R, and that's that's a way in which you can convert between Cp and Cv. And then we have now here where we're showing that we are also showing that Cp over Cv, or the ratio of Cp to Cv, is equal to this constant, which is called the adiabatic index, or the Poisson constant, which can be quite useful, and you will learn about that later in more advanced thermodynamic courses. What about reversible and irreversible system? We want to talk about reversible versus irreversible pathways, or reversible versus irreversible systems. Now, there's a distinction to be made in describing the path or pathways of perfect gas processes, either as reversible or irreversible pathways. Now, a reversible path is one in which a system is at equilibrium at every stage of the process. Right? That is a reversible path. It is at equilibrium at every stage of the process. Now, of course, you have irreversible systems, and irreversible systems are described as systems which are at equilibrium only at the beginning or at the initial and final stages of the process, and not in between. Right? So they are not at equilibrium at all stages of the process, just at the beginning and at the end. Now that is very important, and you'll see more about that later on. Now, when we speak of an isothermal reversible process, we mean that the process follows a path that has the system at the same temperature, because that's what isothermal means. Iso means the same. Thermal, we're talking about temperature, so it means same temperature. So when we talk about an isothermal reversible process, we mean that the process follows a path that has the system at the same temperature at every stage of the process, and in addition to that, the system is at equilibrium at every stage of the process. Now, an isothermal irreversible process is one in which a system has been moved from an initial state to a final state, with the final state having the same temperature as the initial state. But the path followed is one in which the system is not at equilibrium at every stage of the process, just at the beginning and at the end. And that is important, and you will see more about that in subsequent lectures. Now let's look at a PV diagram, a pressure volume diagram for a reversible system versus an irreversible system. Now on our left, we have a pressure volume diagram for a reversible system. Now this system is at equilibrium at every step. Hence, PV, the product of pressure and volume, is equal to a constant. That constant is called nRT, number of moles times the universal gas constant times temperature. And what this means is that you could use this relationship to do calculations or to make predictions of reversible systems. Now, for irreversible systems, PV is not equal to a constant all throughout the process, just at the beginning and at the end, not throughout the entire process, just at the beginning and at the end. Now, to calculate the work for done by an irreversible system or done by a gas under irreversible conditions, the work is equal to minus P delta V, which is basically the area beneath the curve. For the reversible system, we have to do something else to determine the work. The work is equal to minus nRT ln V final over V initial, that equation which we derived previously. So the work is calculated differently. However, for both cases, the work is just equal to the area beneath the curve, alright, in both cases. However, they are calculated differently. Okay, so that is important to note. Let's just explain something that is very important. Isothermal. Let's get a little bit deeper into this. Now, isothermal means constant temperature or same temperature. That is, delta T is equal to 0. Now, when delta T is equal to 0, the internal energy is also fixed. That is, delta U is equal to 0. This tells us that minus Q, that is, any heat lost by the system, must be replaced by work done on the system. Now let's consider this. Let's consider a system with some gas particles. Gas particles in a container, alright, covered by a movable piston. Okay? Our container contains, what's this? 5, 6, 9 particles. So we have about 9 particles there in our system. Alright, a matter of fact, 9, no, that's 10. We have 10 particles. We have 10 particles in our system. 5 down here, 6 and 4, 10 particles in our system. Now, let's say our system is structured, or it exists between two reservoirs. It exists between a hot reservoir and a cold reservoir. If our system loses heat energy to the cold reservoir, that is, heat travels from our system to the cold reservoir, that is, we are losing heat energy. How then can the temperature remain constant? If the system is losing heat energy, how is it that the temperature is going to remain constant? Well, the heat energy that is being lost must be replaced some way, somehow. The way in which we can replace that heat energy is by compressing the system, pushing down on that movable piston. And we have to compress the system, that is, we have to do work on the system that is equal to the amount of heat lost. What I am saying is that if the system loses 50 kilojoules of heat, then 50 kilojoules of work must be done on the system. If this is done, the temperature will remain constant, because the heat loss, which will be minus 50 kilojoules, will be replaced by plus 50 kilojoules of work. Hence, delta U is equal to 0. And hence we say that we have an isothermal system. Let's differentiate, let's mention, or let's differentiate or discuss different types of systems. Now, there are different, we have been talking about different systems. We have been using the term systems. Let's define, or let us get more intimate with this term. There are different types of systems, first of all. You have open systems, which are able to exchange both energy and matter with the surroundings, right? So open systems are able to exchange both energy and matter with its surroundings. Then we also have closed systems, which are not able to exchange matter, but they are able to exchange energy. Such a system is able to exchange energy, but not matter with its surroundings. We also have isolated systems. Isolated systems are not able to exchange anything with the surroundings. That is, they are not able to exchange matter, and they are not able to exchange energy with their surroundings. These systems are kind of difficult to put together. They are more theoretical in nature. Then we also have now a special system called an adiabatic system. Right? It's called an adiabatic system. Now, this is a system which is unable to exchange heat energy with its surroundings. However, this system can do work. It's a very important system. So it is unable to exchange heat energy, that is, no heat energy can enter or leave such a system. However, it is able to do work. Alright, and these are the main types of systems. Now, if we should look at a plot, a PV diagram, right, a pressure volume plot for isothermal reversible systems and also adiabatic reversible systems, we will notice that there is something interesting. The adiabatic system will always have a steeper curve than the isothermal system. Why is that? Why is that? We need to be able to explain this. Now, if you think about having a gas in a container. Right? The gas is in a container, and let's say you have a movable piston. We're going to discuss the isotherm first. We have a movable piston. Isotherm means that the temperature is fixed, so the temperature is not changing. Let's say the gas is expanding. Expanding simply means that its volume is increasing. If the volume is expanding, that is, the gas is expanding, volume is increasing, the particles are moving further and further away from each other. Right? So the gas is expanding. Expansion means that the gas is doing work. If the gas is doing work, then its internal energy should decrease. However, if its internal energy is to remain fixed, then you have to put heat energy into the system. And this is what happens for isotherm. So the isothermal system, right, under isothermal conditions, the gas is expanding, that is, it is doing work, and therefore it is using up its internal energy. However, that which it is using up is being replaced continuously by the input of heat energy. So any energy lost as a result of doing work is being replaced by the input of heat energy. And so what you find, even though the isotherm is expanding, its pressure will drop, but very gradually. It will not drop rapidly. So there's a decrease in pressure, but that decrease is not very rapid, because even though the gas particles are moving further from each other, that is, they are expanding, using up energy, doing work, the energy being lost is being replaced. The energy being consumed as work, as the gas does work, is being replaced by the input of heat energy. In the case of an adiabatic system, though, as the gas expands, that is, as the gas continues to do work, there is no input of heat energy. Right? Because remember, adiabatic system cannot absorb heat energy from outside, and also it cannot release heat energy to the outside. So what you find is that as the gas is expanding under adiabatic conditions, it is doing work, and therefore its internal energy is decreasing. This will cause the gas to cool. That is, the gas particles will lose kinetic energy. Their kinetic energy will decrease, because remember what temperature is. Temperature is a measure of the average kinetic energy of particles in a body. So if the gas is doing work, right, and is therefore using up its internal energy, the gas will start to cool. If it is cooling, it means that its kinetic energy is decreasing. Therefore, the particles are not colliding with each other very frequently. Right? Or let's say the frequency with which they collide with each other is decreasing. Also, the frequency with which they collide with the walls of the container is decreasing significantly. Therefore, the effect that they have, the pressure that they create, which comes from collision of the walls of the container, will decrease rapidly. Hence, for the adiabat, as the gas expands, the pressure drops rapidly. And hence, the adiabat, the PV plot for the adiabat is always steeper than the isotherm. I hope this lecture was helpful. Be sure to post your questions, if any.